Hello there, and welcome to the Dozing Explorer. I am so glad you have found your way here tonight, to this quiet place of rest. There is nothing you need to do now, nothing to figure out. Simply find a comfortable position, close your eyes if you wish, and allow my voice to be a soft anchor for your wandering mind. Tonight, we are going to drift into the deep and silent mysteries of black holes. We will not treat them as objects of fear, but as places of profound calm and simplicity. We will wander near their quiet edges where the laws of the universe become gentle and strange. This is not a lesson, but a journey into the soft, perfect darkness, an exploration of the universe's most patient and mysterious creations. We will think of them not as voids, but as the universe in a state of deep and silent meditation. We will float through the gentle way they bend light and the slow, graceful way they warp the flow of time. We'll listen to the idea that they are not cosmic monsters, but the natural and peaceful endpoint for the grandest stars, the final, quiet state of matter. This is a journey to the very edge of understanding, a place where physics becomes a form of poetry and where the most complex ideas resolve into the simplest of forms. And just before we begin our drift, if these quiet explorations help you unwind and find your rest, please consider liking and subscribing. It is a silent gesture that helps other sleepy souls find their way to this sanctuary, and it ensures that our journeys can continue. But for now, all of that can fade away. There is nothing you need to know or remember. Your only task is to rest, to breathe in and to breathe out. Settle in, get comfortable, and let the journey begin. You have permission to let go, to drift, and to fall completely and deeply asleep whenever you are ready. A black hole makes no sound. In the vast theater of the cosmos, the formation and existence of a black hole is a completely silent event. Sound requires a medium to travel, like air or water, but the vacuum of space is a place of profound quiet. Even the collapse of a colossal star, an event of unimaginable power, happens without a whisper. The black hole drifts in this perfect, unbroken silence, an object of immense gravity and utter stillness, making no noise at all as it moves through the cosmic dark. It is the universe's most profound event, wrapped in a perfect and unending quiet. Time behaves differently near a black hole, slowing down the closer you get. According to Einstein's theory of relativity, gravity is a curvature in the fabric of space-time, and this curvature affects the flow of time itself. Imagine time as a gentle river. Near a black hole, the current of that river becomes deep and slow. A clock placed near a black hole would tick more slowly than a clock far away. For an astronaut orbiting close to the edge, only minutes might pass while decades or centuries go by for the rest of the universe. It is a place where the rhythm of the universe itself begins to slow to a gentle, graceful halt. The nearest black hole is over 1,000 light-years away from us. While the universe is filled with these mysterious objects, none are close enough to be of any concern to us. The closest known black hole, named Gaia BH1, is so distant that the light from its neighborhood takes more than 1,500 years to reach us. It is a quiet and distant neighbor, a silent resident of our galaxy that we can observe with our telescopes from a position of absolute safety. They are distant, quiet neighbors in our vast galactic city. If our sun were replaced with a black hole of the same mass, the Earth's orbit would not change. This is a common misunderstanding about black holes. Their gravitational pull depends only on their mass and your distance from them, not on their exotic nature. Since a solar mass black hole would have the exact same mass as our sun, its gravitational influence on the planets would be identical. The Earth and all the other planets would continue in their familiar, stable orbits, feeling the exact same gentle tug of gravity as they do now, simply circling a point of perfect darkness instead of a brilliant star. The familiar waltz of the planets would continue undisturbed around a new, silent partner. Black holes are not cosmic vacuum cleaners. You have to be very close to fall in. Unlike the way they are often portrayed, black holes do not travel through space, actively sucking up everything around them. They obey the same laws of gravity as any other object. You could fly past a black hole at a safe distance, and it would simply feel like flying past a normal star of the same mass. It is only when you cross a very specific boundary, very close to the black hole, that escape becomes impossible. They are passive, patient objects, not aggressive hunters. It is a quiet harbor that you must deliberately steer your ship into. The edge of a black hole is a calm and quiet place called the event horizon. This is not a fiery, chaotic wall, but a completely invisible and placid boundary in space-time. There is no surface to hit, no matter to collide with. It is simply a point of no return. As you approach it, space itself is flowing inward, and the event horizon is the point where the speed of that inward flow surpasses the speed of light. It is a silent, one-way door in the fabric of the universe. It is a waterfall's edge where the river of space-time begins its final, gentle cascade. An event horizon is a boundary of information, not a physical surface. The event horizon is a mathematical concept, a consequence of gravity's effect on light. It is the boundary that separates the observable universe from the part of the universe from which no information can ever return to us. Anything that crosses it, including light, is unable to send a signal back out. It is not a thing you can touch, but a concept you can cross, a perfect and smooth transition from one region of space-time to another. It is less a wall and more a veil separating the known from the unknowable. Some black holes are only a few miles wide. The size of a black hole's event horizon depends on its mass. A stellar mass black hole, one formed from the collapse of a single star, might have a mass a few times that of our Sun. All of that mass is concentrated in a region of space-time so small that the event horizon would only be about 10 or 20 miles across. An entire star's worth of matter existing within a space no larger than a city. It is a testament to the incredible power of gravity to compress matter into its most compact possible form. Supermassive black holes exist at the center of nearly every large galaxy, including our own. At the heart of the vast spinning cities of stars we call galaxies, there lies an object of immense scale. These are supermassive black holes with masses ranging from millions to billions of times that of our Sun. They are the quiet gravitational anchors around which entire galaxies revolve. They did not form from a single star, but likely grew over billions of years, merging with other black holes and slowly accreting gas and dust. They are the calm and silent centers of the galactic storm. The black hole at the center of the Milky Way is named Sagittarius A.K. Our home galaxy has its own gentle giant at its core. Located about 27,000 light-years away in the direction of the constellation Sagittarius, this supermassive black hole is a place of relative quiet. For now, it is not actively feeding on large amounts of material, so it is not a bright and violent quasar. It is a sleeping giant, the silent, invisible heart around which our entire galaxy gracefully spins. It is the quiet center of our galactic home. From a safe distance, you could orbit a black hole just as you would a star. The laws of orbital mechanics are the same for all objects. If you were in a spaceship at a stable distance, you could enter into a perfect, calm orbit around a black hole. You would feel no strange forces, no sense of being pulled in. You would simply follow a gentle, elliptical path through the curved space-time with the perfect darkness of the black hole hanging in your sky like a silent, unblinking moon. It would be a place of deep and profound gravitational peace. Black holes are born from the silent collapse of the largest stars. When a star more than 20 times the mass of our Sun runs out of fuel, its own gravity overwhelms it. The core of the star collapses in on itself in a fraction of a second, an event of unimaginable speed and power that happens in complete silence. If the core is massive enough, nothing can stop the collapse, and it continues until a black hole is formed. It is a natural and peaceful endpoint for the most majestic of stars. It is the universe's way of turning a star's light into a quiet and eternal shadow. The black part of a black hole is a perfect darkness caused by gravity. The object itself is not made of some dark material. It is black because its gravity is so powerful that it has curved space-time back on itself. Light, which always travels on the straightest possible path through space-time, follows this curve and cannot escape. The blackness is not a color, but an absence of light, a region of space from which no illumination can return. It is the deepest, most perfect shadow in the entire universe. Light that falls into a black hole cannot escape. Imagine trying to throw a ball out of a deep well. The deeper the well, the faster you have to throw it to escape. A black hole is a well in space-time so deep that the speed you would need to escape is faster than the speed of light. Since nothing in the universe can travel faster than light, nothing, not even light itself, can make the journey back out. It is the universe's ultimate one-way path. A black hole's gravity bends the space around it like a heavy ball on a soft sheet. This is the central idea of Einstein's theory of general relativity. Mass does not create a pull, but rather it tells space-time how to curve. Space-time, in turn, tells other objects how to move. A black hole is an object of such immense mass in such a small space that it creates a very deep and steep curve in space-time around it. Other objects, and even light, simply follow the gentle, sloping contours of this curve. It is a quiet, deep valley in the landscape of the cosmos. This bending of space can create a gravitational lens, magnifying distant galaxies. If a black hole passes directly between us and a very distant galaxy, its gravity can act like a lens. The light from the distant galaxy is bent and redirected around the black hole, often creating multiple, distorted, and magnified images of the galaxy. This beautiful and strange effect, called gravitational lensing, allows us to see objects in the distant universe that would otherwise be too faint to observe. The black hole becomes a natural telescope for viewing the deep cosmos. Black holes can sing a deep note, not in sound, but in gravitational waves. While black holes are silent in the traditional sense, the merger of two black holes is an event of such gravitational violence that it creates ripples in the very fabric of space-time. These gravitational waves travel outward at the speed of light. Our detectors can translate these faint ripples into a sound wave, and the result is a gentle, rising chirp that lasts for less than a second. It is the only sound that a black hole can ever make, a quiet song sung in the language of gravity itself. The properties of a black hole are incredibly simple: mass, spin, and charge. A star is a complex object with a unique chemical composition, temperature, and structure. But when it collapses to form a black hole, all of this complexity is lost. All that remains are three fundamental and simple properties. We can know its total mass, how fast it is spinning, and its overall electric charge. Everything else about the matter that formed it is forgotten. It is the universe's ultimate state of simplicity. At the event horizon, time slows to a complete stop from an outside perspective. This is the strange effect of gravitational time dilation taken to its extreme. For a distant observer watching an object fall towards a black hole, the object would appear to slow down as it gets closer to the event horizon. It would seem to take longer and longer to cross that final boundary, its light becoming redder and dimmer, until it appears to be frozen in time forever, perfectly preserved at the edge. The final moment of its fall would be stretched out for all of eternity. Black holes were first imagined using only pen, paper, and the theory of relativity. Long before we had any observational evidence for them, their existence was predicted by physicists studying the mathematical equations of Albert Einstein's new theory of gravity. Carl Schwarzschild found the first exact solution that described what we now call a black hole just a year after Einstein published his theory. It was an object so strange that it was considered a mathematical curiosity for decades before we realized the universe actually makes them. Their existence was discovered first in the quiet world of pure thought. There may be billions of black holes drifting silently through our galaxy alone. Based on the number of massive stars that have lived and died over the Milky Way's history, astronomers estimate that our galaxy is filled with these stellar remnants. Most are isolated and do not have a companion star or a gas cloud to feed on, so they are completely invisible. They are a silent, unseen population of objects, drifting patiently through the darkness between the stars. The galaxy is filled with these quiet, sleeping ghosts. Spaghettification is a gentle term for the stretching caused by a black hole's gravity. As an object gets very close to a small stellar mass black hole, the gravitational pull on the part of the object closer to the black hole is significantly stronger than the pull on the part farther away. This difference in gravitational force, known as the tidal force, would gently stretch the object out into a long, thin strand, like a piece of spaghetti. It is a quiet and inexorable process of gravitational stretching. For supermassive black holes, you could cross the event horizon without feeling a thing. The tidal forces of a black hole are actually much weaker for the supermassive kind. Because their event horizons are so large, the difference in gravity between your head and your feet as you cross the boundary would be negligible. The crossing would be a completely calm and uneventful moment. You would simply drift across this invisible line, feeling no force, no stretching, unaware that you had just passed the point of no return. It would be the most peaceful and profound transition imaginable. Nothing in the universe can travel faster than light, which is why nothing escapes. The speed of light is the ultimate cosmic speed limit, woven into the fabric of space-time. The event horizon of a black hole is simply the place where the escape velocity, the speed you need to get away, becomes greater than this cosmic limit. It is not that the black hole has a mysterious power, but simply that the laws of physics themselves forbid any object from achieving the speed necessary for escape. The boundary is created by a fundamental rule of the universe. The first ever image of a black hole was captured in 2019. Using a network of radio telescopes spread across the entire globe, effectively creating a virtual telescope the size of the Earth, a project called the Event Horizon Telescope was able to capture an image of the supermassive black hole at the center of the galaxy M87. It was a monumental achievement, the culmination of decades of work by hundreds of scientists. For the first time, we could see the unseeable. This image showed the shadow of the black hole, not the object itself. Because a black hole emits no light, it cannot be photographed directly. What the famous image shows is the bright, glowing ring of superheated gas orbiting the black hole. In the center of that ring is a dark region, a silhouette. This is the shadow that the black hole casts upon the light behind it, a region where the black hole's gravity has captured all the light, creating a perfect circle of darkness. We are seeing the hole's gentle fingerprint on the light of the cosmos. Black holes can slowly evaporate over trillions of years through a process called Hawking radiation. Stephen Hawking discovered that due to quantum effects near the event horizon, black holes are not perfectly black. They should emit a faint, constant stream of particles. This process, known as Hawking radiation, causes the black hole to lose mass over incredibly long periods of time. It is a slow, patient process of giving its energy back to the universe. This faint radiation is like the black hole's subtle warmth. Every object with a temperature radiates energy. The Hawking radiation of a black hole gives it an effective temperature. This temperature is infinitesimally small, far colder than the background temperature of space, but it is not absolute zero. It is a sign that black holes are not eternal prisons, but dynamic objects that are slowly, gently, and quietly dissolving back into the fabric of space-time. They have a faint, theoretical warmth, a soft glow on a quantum level. The smallest black holes will evaporate the fastest. The rate of Hawking radiation is inversely proportional to the black hole's mass. This means that a smaller black hole is actually hotter and will evaporate much more quickly than a large one. A hypothetical black hole with the mass of a mountain might evaporate in a brilliant flash of energy, while a supermassive one will take an unimaginably long time to fade away. The largest black holes will take longer than the current age of the universe to disappear. A supermassive black hole is so large and so cold that its rate of evaporation is incredibly slow. The time it would take for one of these galactic giants to radiate away all of its mass is a number so large it is almost meaningless, many trillions upon trillions of times the current age of our universe. They are the most stable and long-lasting objects in the entire cosmos. Their quiet existence will likely outlast all of the stars. A black hole does not have infinite density, but a singularity of unknown physics. At the very center of a black hole, our current theories predict a point of zero volume and infinite density, called a singularity. However, this is likely a sign that our theories of gravity and quantum mechanics are incomplete. At this central point, the laws of physics as we know them simply break down and can no longer describe reality. It is not necessarily a point of infinity, but a place where our current understanding finds its quiet and humble limit. The laws of physics as we know them break down inside a black hole. General relativity and quantum mechanics are our two great pillars of modern physics, but they do not work together. Inside a black hole, where immense gravity meets the tiniest of scales, both theories would be needed, but they give contradictory answers. To understand what truly happens at the center, we would need a new theory, a theory of quantum gravity. The interior of a black hole represents one of the greatest and most peaceful frontiers of human knowledge. Black holes can spin, some of them at nearly the speed of light. When a massive, rotating star collapses, its spin is conserved and transferred to the black hole it becomes. This can result in a black hole that is spinning at a tremendous rate. The event horizon of a spinning black hole is not a perfect sphere, but is slightly flattened at its poles. This spin adds a new layer of complexity and strange beauty to the object's properties. A spinning black hole drags the fabric of space-time around with it. This is one of the strangest predictions of general relativity. A rotating massive object does not just sit in space-time, it twists space-time around it like a spinning ball in a vat of honey. This effect, called frame dragging, means that there is no such thing as standing still near a spinning black hole. The space itself is in motion, and everything within it is gently and irresistibly carried along with the spin. This effect is called frame dragging. The term refers to the way the black hole's spin drags along the local inertial frame, the very reference frame of what it means to be at rest. Close to the spinning black hole, the fabric of space-time is moving so fast that you would have to travel faster than light to remain stationary from a distant observer's point of view. It is a gentle, cosmic whirlpool in the very substance of space. There may be a calm region inside a spinning black hole's event horizon. The mathematics of spinning black holes predict a strange and complex interior structure. Inside the outer event horizon, there may be a second inner horizon. The region between these two horizons is a place where some of the bizarre effects of the singularity are softened It is a theoretical region of relative calm, a peaceful inner sanctum hidden deep within the black hole's core, primordial. Black holes may have formed in the first moments after the Big Bang, in the incredibly dense and chaotic environment of the very early universe. It is possible that small regions of matter could have been compressed enough by the surrounding pressure to collapse directly into black holes. These primordial black holes would not have come from stars and could have a vast range of masses, some perhaps even smaller than an atom. They are a population of ancient, theoretical objects, the oldest black holes in the universe. These ancient black holes could be smaller than an atom. A primordial black hole with the mass of a large asteroid would have an event horizon smaller than a single proton. These tiny, ancient objects, if they exist, would be drifting silently through the universe, completely invisible. They are a gentle and hypothetical reminder that some of the most profound objects in the cosmos might also be the very smallest. The concept of a black hole was so strange that even Einstein was skeptical of it at first. Although his own theory of general relativity predicted their existence, Albert Einstein thought that they were a mathematical oddity that would never actually form in the real universe. He believed that some other physical principle would intervene to prevent a star from collapsing to such an extreme state. It was only decades later that the theoretical and observational evidence became so strong that their existence was accepted as a reality. Even the mind that imagined them found their quiet reality hard to believe. Black holes do not grow forever. They are limited by the material available to them. A black hole can only grow in mass if matter falls into it. The supermassive black holes at the centers of galaxies grew to their immense size during the early, chaotic, and gas-rich history of the universe. In our current, more sedate era of the cosmos, there is much less free-floating gas and dust available. Most black holes are now in a state of quiet fasting, no longer growing, but simply existing in a patient and peaceful equilibrium with their surroundings. An accretion disk is a glowing ring of gas that orbits a black hole like water circling a drain. When a black hole is actively feeding, the gas and dust it pulls in do not fall directly. Instead, they form a vast, flattened, spinning disk of material. The friction between the particles in this disk heats them to incredible temperatures, causing them to glow with a brilliant light. This is the source of the immense energy we see from quasars and other active galactic nuclei. The gas in an accretion disk gets hotter the closer it is to the event horizon. As the material in the disk spirals inward, it loses energy and heats up. The innermost regions of the disk, just before the gas takes its final plunge across the event horizon, can reach temperatures of millions of degrees. This is why these disks shine so brightly, particularly in X-rays. It is the brilliant light of matter's final warm embrace before it returns to a state of simplicity. This heat makes accretion disks some of the brightest objects in the universe. A single accretion disk around a supermassive black hole can outshine its entire host galaxy of billions of stars. The process of converting the gravitational potential energy of falling matter into light is the most efficient energy generation mechanism known in the universe, far more efficient than the nuclear fusion that powers stars. It is a light powered by the gentle, inexorable pull of gravity itself. The black hole itself remains perfectly dark in the center of this brilliant light. This is the beautiful paradox of an active black hole. It is the source of some of the most luminous phenomena in the cosmos, yet the object at the heart of the storm remains a place of perfect, calm darkness. The brilliant light of the accretion disk serves only to highlight the profound and quiet emptiness of the black hole's shadow. At its center, two black holes can orbit each other for billions of years in a silent dance. In the crowded centers of galaxies, it is common for two black holes to become gravitationally bound to each other. They will enter into a long, stable orbit, a binary pair of silent, dark objects. Over immense timescales, they will slowly spiral closer and closer together as they radiate away their orbital energy in the form of faint gravitational waves. It is the most patient and graceful waltz in the entire cosmos. When two black holes merge, they release more energy than all the stars in the universe combined. The final moments of their long spiral are a truly cataclysmic event. In the fraction of a second that the two event horizons touch and merge into one, a colossal amount of their mass is converted directly into pure gravitational energy. For that brief instant, the merger is the most powerful event happening anywhere in the universe. This energy is released not as light, but as ripples in space-time. The merger of two black holes is a completely dark event. There are no stars or gas to create a flash of light. The entire unimaginable release of energy is in the form of gravitational waves, a silent storm in the fabric of space-time itself. It is a profound event that passes by without any visible sign, a quiet shudder in the cosmic landscape. These ripples are called gravitational waves. Predicted by Einstein a century ago, these waves are disturbances in the curvature of space-time, traveling outward from their source at the speed of light. They are a completely new way for us to observe the universe, a way to sense the silent, dark events that our telescopes can never see. They are a testament to the fact that even the quietest and darkest corners of the universe can send us a gentle message. Gravitational waves were first detected in 2015, confirming a century-old prediction of using incredibly sensitive laser interferometers. Scientists were able to detect the minuscule stretching and squeezing of space-time caused by the gravitational waves from two merging black holes over 1 billion light-years away. It was a Nobel Prize-winning discovery that opened a brand new window onto the cosmos, allowing us to listen to the silent, gravitational universe for the very first time. The sound of two merging black holes is a gentle chirp that lasts less than a second. When the gravitational wave signal is converted into an audio signal, it has a distinct and beautiful sound. It starts as a low rumble that rapidly increases in both pitch and volume, ending in a final high-pitched chirp as the two black holes finally merge into one. This brief and simple sound is the final note in a gravitational dance that lasted for billions of years. It is the quiet and gentle song of two great masses finally becoming one. Stars can be seen orbiting the invisible center of our galaxy, revealing the black hole's presence. We know that the supermassive black hole Sagittarius A lies at the heart of the Milky Way, not by seeing it, but by watching its quiet influence on the stars closest to it. For decades, astronomers have patiently tracked the movements of a small cluster of stars right at the galactic core. These stars are moving at astonishing speeds, some traveling at millions of miles per hour, as they whip around a central point that contains no visible light. Their paths are graceful and precise, following the exact orbits predicted by the laws of gravity if they were dancing with a single, massive, and unseen object. They are dancers in the dark, their movements revealing the presence of their silent, unseen partner. These stars follow perfect, calm, elliptical orbits. The paths of these stars at the galactic center are not chaotic or messy. They are smooth, predictable, and stable, following the clean lines of an ellipse just as the planets orbit our sun. This serene and orderly motion is a crucial piece of evidence. If the 4 million solar masses at the galaxy's heart were spread out among a large cluster of smaller objects or a vast cloud of gas, the gravitational field would be lumpy and uneven, and the orbits of these stars would be wobbly and disturbed. The calmness and perfection of their dance is the strongest proof that the object they orbit is a single, compact, and quiet, supermassive black hole. Their serene and steady paths are a testament to the simple, pure gravity at the galaxy's heart. The information that falls into a black hole might not be lost forever. This is the heart of a deep and beautiful puzzle in physics known as the black hole information paradox. One of the fundamental rules of quantum mechanics is that information about an object can never be truly erased from the universe. Yet, a black hole seems to be the ultimate vault, a place where things go in but never come out. To solve this, many physicists, including Stephen Hawking in his later work, came to believe that the information is not destroyed. Instead, it might be delicately imprinted or encoded onto the surface of the event horizon, like a faint, two-dimensional hologram preserving the story of everything that has ever fallen inside. The universe, it seems, is a careful librarian that never truly throws a book away. The holographic principle suggests information is stored on the event horizon's surface. This profound idea emerges from the puzzle of black hole information. It proposes that all the information needed to describe a three-dimensional volume of space can be thought of as being encoded on its two-dimensional boundary. For a black hole, this means the entire complex, three-dimensional story of every particle that falls in can be stored on the simple, two-dimensional surface area of its event horizon. It is a deep and strange idea that suggests our seemingly solid, three-dimensional world might itself be a projection of information from a distant, flatter reality. The surface of a black hole might be the universe's most efficient storage device. If you fell into a black hole, your past and future could become a single direction in space. Inside the event horizon, the fabric of space-time is warped to an incredible extreme. The direction that we normally think of as forward in time becomes a spatial direction, one that points inevitably toward the singularity at the center. At the same time, the three spatial dimensions we know, forward, left, right, can become jumbled with time. It is a place where our familiar notions of space and time gently dissolve, where the journey forward in distance and the journey forward in time become one and the same quiet, inevitable path. The flow of time becomes a place you can travel to. The sky above you would shrink to a single bright point of light. For a hypothetical traveler crossing the event horizon, the view of the outside universe would become strange and beautiful. Because of the extreme bending of light, the entire view of the external cosmos, all the stars, all the galaxies, all of cosmic history, would appear to be concentrated into a small, brilliant circle of light directly above. As you continued to fall inward, this window to the universe would shrink, becoming brighter and more blue-shifted, a final, concentrated glimpse of all that ever was and ever will be, compressed into one single, serene point. It is a final, peaceful vision of the entire universe gathered into one place. The term black hole was coined by the physicist John Archibald Wheeler in 1967. For more than 50 years after their prediction by theory, these objects had no simple, evocative name. Scientists referred to them with cumbersome phrases like gravitationally completely collapsed objects. During a conference, Wheeler, who was known for his gift for language, offered the simple, powerful, and poetic term black hole. It was a name that perfectly captured the object's two most essential features, its gravitational power and its inability to emit light, and it has remained with us ever since. It was a name that gave a simple handle to an infinitely complex idea. Before that, they were sometimes referred to as frozen stars. This earlier name came from the strange effects of gravitational time dilation. To a distant observer, an object falling into a black hole would appear to slow down and freeze at the event horizon, its light becoming redder and dimmer until it faded away completely. From our perspective, the formation of the black hole would be an event stretched out over an infinite amount of time, and so the star would appear to be frozen at the very moment of its collapse. It is a beautiful name for a star locked forever in its final moment of becoming. A black hole's gravitational pull is the same as a star of the same mass from a great distance. Far away from the event horizon, a black hole's gravity behaves in a completely ordinary and predictable way. It is no stronger or more mysterious than the gravity of any other object. If you are 1,000,000 miles from a black hole that has the mass of our Sun, you feel the exact same gentle gravitational tug as you would 1,000,000 miles from the Sun itself. The strangeness of a black hole is a very local phenomenon. From a distance, it is just another quiet and well-behaved citizen of the galaxy. Black holes play an important role in how galaxies are formed and grow. The supermassive black holes at the centers of galaxies are not just passive anchors, they are active participants in the life of their host galaxy. As they feed on gas and dust, they can release enormous amounts of energy back into the galaxy in the form of powerful jets and winds. This outflow of energy can be a gentle and regulating force, shaping the entire ecosystem of the galaxy around it. They are like the gentle gardeners of their galactic homes. The powerful jets from a black hole can stop new stars from forming, regulating a galaxy's size. Sometimes a galaxy can become so filled with cold gas that it would otherwise form stars at a runaway rate. The energy blasted out from the central supermassive black hole can heat up this gas, preventing it from collapsing to form new stars. This process, known as feedback, creates a delicate balance, ensuring that the galaxy does not grow too large or too quickly. The black hole acts as a gentle thermostat, keeping the entire galaxy in a state of calm and stable equilibrium. A photon sphere is an area where light itself can orbit a black hole. Just outside the event horizon, there is a region of space where gravity is so strong that photons of light can be forced to travel in circles. Light is not captured and pulled in, but it is not free to escape either. It can become trapped in a temporary circular orbit, like a tiny moon made of pure light. This sphere of orbiting light is a shimmering theoretical boundary around the black hole's deeper darkness. Light in the photon sphere follows a circular, stable path. A beam of light entering this region at just the right angle could theoretically orbit the black hole forever. It would circle the profound darkness at its center, a perpetual ring of captured light. If you were somehow able to exist at this photon sphere and look straight ahead, the path of light would be so curved that the photons from the back of your head would travel all the way around the black hole and arrive at your eyes from the front. It is a place where looking forward allows you to see behind you. If you stood in the photon sphere, you could see the back of your own head. This strange and beautiful consequence of curved spacetime is a classic thought experiment. Because light can orbit at this distance, the light leaving the back of your head could complete a full circle around the black hole and enter your eyes from the front. You would be surrounded by a distorted, ghostly image of yourself, a view of your own past captured and returned to you by the gentle, bending power of gravity. It is a place where space itself becomes a perfect and silent mirror. Intermediate mass black holes are a missing link that astronomers are searching for. We have found plentiful evidence for small stellar mass black holes and for the supermassive giants at the centers of galaxies. But there is a mysterious gap in between for black holes that are hundreds or thousands of times the mass of the Sun. Finding these intermediate mass black holes is a major quest in astronomy, as they would help us understand how the supermassive ones grew to their immense sizes. They are the quiet, missing members of the black hole family. The process of falling into a black hole is a one-way journey. Once an object crosses the event horizon, its future is sealed. This is not because of a powerful force pulling it in, but because the fabric of space-time itself is flowing inward faster than the speed of light. To escape would not be a matter of having a powerful engine. It would be a matter of traveling backwards in time, something the laws of physics do not seem to permit. It is the universe's most gentle and absolute form of inevitability. The event horizon is sometimes called the point of no return. This name perfectly captures its essential nature. It is not a wall or a membrane, but an invisible threshold in space-time. Before you cross it, you are free to leave. After you cross it, you are not. It is a quiet and unassuming border between the rest of the universe and a small, private region of space-time from which escape is not possible. It is a gentle line drawn in the cosmos from which there is no retreat. From your perspective, time would continue normally as you crossed the event horizon. For a person falling into a black hole, nothing special would seem to happen at the moment of crossing the event horizon. Your watch would continue to tick at its normal rate, and your thoughts would proceed, as they always do. The laws of physics in your immediate vicinity would be unchanged. The profound nature of the boundary you had just crossed would be completely imperceptible to you. It is a moment of immense significance that would feel like nothing at all. An outside observer, however, would see you appear to freeze in time forever. This is the great paradox of black hole physics. While your own journey inward would be swift, anyone watching you from a safe distance would see a very different story. As you approach the event horizon, they would see your image slow down, your light signals becoming redder and taking longer to arrive. You would appear to hover at the edge, frozen for all of eternity, slowly fading from view as your final light signal is stretched out over an infinite amount of time. You would become a permanent fading ghost on the edge of space-time. This is because your light signals would take longer and longer to escape. As you get closer to the event horizon, the pull of gravity becomes stronger, and the light you emit has to struggle harder and travel a more curved path to escape. From a distant observer's point of view, each successive photon you emit takes a little bit longer to arrive than the one before it. This stretching out of the time between light signals is what creates the illusion of your time slowing down and eventually stopping completely. Your story, from the outside, would become a story that never quite reaches its end. The final light signal you emit would take an infinite amount of time to leave the horizon. The very last photon you emit just as you cross the event horizon is in a unique position. It is trying to escape from a place where the exit speed is exactly the speed of light. It will therefore travel outward, but make no progress, forever balanced on that quiet edge. From a distant perspective, it is a signal that will never arrive, a final message suspended for all of eternity. Black holes represent the ultimate victory of gravity over all other forces. Throughout the universe, there is a constant battle between gravity pulling things together and other forces, like the pressure of gas or the quantum forces within atoms pushing things apart. A black hole is a place where this battle has been completely and decisively won by gravity. All other forces have been overwhelmed, and matter has been compressed into its ultimate, final state, a quiet monument to the patient and relentless power of gravity. The material a black hole is made from is forgotten. Only its mass, spin, and charge remain. It does not matter if a black hole was formed from a star made of hydrogen, a planet made of iron, or a spaceship made of exotic alloys. Once the material crosses the event horizon, all of its unique properties and complexities are erased. The black hole only remembers the total mass that was added, any rotation it had, and any electrical charge it carried. It is a process of profound and peaceful simplification. This is known as the no-hair theorem. This poetic name was given to the idea that black holes are remarkably simple objects. The hair is a metaphor for all the other complex properties that an object can have, such as its chemical composition or its surface features. The theorem states that a stable black hole has no such hair. It is perfectly bald, described only by its three simple external properties. It is a quiet and elegant statement about the final state of matter. A black hole erases the complexity of the matter it consumes. It is the universe's ultimate equalizer. No matter how intricate or beautiful an object is, once it falls into a black hole, its individual identity is lost to the outside world. It simply contributes its mass, spin, and charge to the whole. This process of erasing complexity is a fundamental aspect of their nature, a return from the intricate forms of the world to a state of profound and featureless simplicity. It is the universe's gentle way of returning things to their most basic form. Our galaxy's supermassive black hole weighs 4 million times more than our Sun. The gentle giant at the heart of the Milky Way, Sagittarius A, has a mass that is difficult to comprehend. It is equivalent to 4 million suns, all compressed into a region of space smaller than the orbit of Mercury. Yet for all its immense mass, it is a place of profound quiet, its gravity serving as the calm and steady anchor for the graceful rotation of our entire galaxy. Despite its great mass, it is still a tiny fraction of the galaxy's total weight. Our Milky Way galaxy, with its hundreds of billions of stars, its vast clouds of gas and dust, and its enormous halo of dark matter, has a total mass of more than 1 trillion suns. The supermassive black hole at its heart, while locally dominant, makes up less than 0.1% of the total mass of the galaxy. It is not the ruler of the galaxy, but rather its quiet, central seed. Black holes do not emit light, but we can detect them by their influence on their surroundings. A black hole on its own is perfectly invisible, but we can infer its presence by its gentle gravitational effects on the things we can see. We can watch a star wobble as an unseen black hole orbits it. We can see the light from a distant galaxy bent as a black hole passes in front of it. We can see the stars at the galactic center swirling around an unseen point of immense mass. They reveal themselves through their quiet, gravitational whispers. They are like an invisible dancer revealed only by the motion of their partner. The most beautiful way we find black holes is by watching a normal visible star that appears to be orbiting nothing. When we see a star performing a graceful periodic dance with an empty point in space, we can deduce the mass and location of its invisible companion. The star's light becomes a beacon, illuminating the presence of the quiet darkness it is bound to. It is impossible to see what is inside a black hole. The event horizon is a perfect cosmic veil. Because no information, not even light, can escape from within it, we can never receive any signal or message from the interior of a black hole. The singularity at its center, and whatever strange physics governs it, will forever be hidden from our direct observation. It is the universe's most perfect and gentle secret. The singularity is hidden from the rest of the universe by the event horizon. This is a fundamental concept known as the cosmic censorship hypothesis. It proposes that every singularity in the universe must be clothed by an event horizon. This means there can be no naked singularities that are visible to the outside universe. This principle keeps the places where our laws of physics break down safely hidden from view, preserving the predictable and orderly nature of the cosmos we can see. It is a gentle cosmic rule that keeps the greatest mysteries perfectly contained. A white hole is the theoretical opposite of a black hole, from which things can only escape. In the mathematics of general relativity, there exists a solution that is the time-reversed version of a black hole. This is a white hole, a hypothetical region of space-time that cannot be entered from the outside, but from which matter and light can emerge. It would be like a fountain in space-time, a source of matter and energy. It is a beautiful and symmetric mathematical idea. There is no evidence that white holes actually exist in our universe. While they are a valid solution to Einstein's equations, we have never observed any phenomenon that would suggest the existence of a white hole. They seem to be a purely theoretical curiosity, a reflection of the beautiful time symmetry in the laws of physics that does not appear to be realized in the actual cosmos we inhabit. They are a gentle ghost in the mathematical machine of the universe. The idea of a black hole is a natural and direct consequence of Einstein's theory of gravity. Black holes are not some exotic, tacked-on idea. They emerge directly and inevitably from the core principles of general relativity. The theory says that mass curves space-time, and a black hole is simply what happens when enough mass is concentrated in a small enough space to curve space-time completely back on itself. They are one of the most profound and gentle predictions of our most beautiful theory of gravity. A black hole warps time as well as space. It is easy to think of gravity as just the bending of space, but Einstein's theory unified space and time into a single, four-dimensional fabric called space-time. A black hole's mass creates a deep well in this fabric, and this well affects both the spatial and temporal dimensions. The slowing of time near a black hole is as fundamental a part of its nature as the bending of light. It is a place where the very rhythm of the universe is altered. The study of black holes pushes our understanding of reality to its absolute limits. These objects are the ultimate cosmic laboratories. They are the places where our theories of gravity, space-time, quantum mechanics, and information are all tested in their most extreme forms. They are the gentle, silent objects that force us to ask the deepest questions about the nature of space, time, and existence itself. They are a quiet guide pointing us toward a deeper understanding of the cosmos. They are perfect, simple, and mysterious objects. A black hole has a kind of profound mathematical perfection. It is an object defined by just a handful of numbers, a pure manifestation of the laws of gravity. It is completely simple in its external properties, yet it hides a deep and ultimate mystery at its core. This combination of perfect simplicity on the outside and profound mystery on the inside is what makes them such compelling and gentle objects of wonder. The light from behind a black hole is bent around it, creating a visual Einstein ring if a bright, distant star or galaxy is perfectly aligned behind a black hole from our point of view. The black hole's gravity will bend the light and redirect it toward us. The light will appear to come from all sides of the black hole at once, forming a perfect, beautiful, and delicate ring of light surrounding the central darkness. It is gravity itself acting as a perfect cosmic lens. The center of a galaxy can be calm and quiet for millions of years. The supermassive black hole at the heart of a galaxy like ours is not always in a state of brilliant, active feeding. For long stretches of cosmic time, there may be very little gas or dust available for it to consume. During these periods, the galactic center is a place of profound peace and quiet, with the sleeping giant at its heart exerting only its gentle, steady gravitational pull. The tidal forces of a small black hole are much stronger than a large one. This is a strange and counterintuitive fact. The stretching force known as spaghettification is most extreme for smaller, stellar mass black holes. This is because their event horizons are so small that the difference in gravity over a small distance is very steep. For a supermassive black hole, the event horizon is so vast that the gravitational field is much flatter, and the tidal forces at the edge are gentle and almost unnoticeable. The larger the black hole, the more peaceful the crossing. Black holes can wander through space after being ejected from a galaxy's center. If two supermassive black holes merge, the resulting single black hole can receive a powerful kick from the gravitational waves that are emitted. This can be enough to eject the newly formed black hole from the center of its own galaxy. These rogue black holes would then wander silently and invisibly through the vast, empty spaces between the galaxies. They are quiet, lonely travelers on an endless journey. The existence of black holes shows that matter can be compressed to an end point. In our everyday world, you can always compress things further. But a black hole represents a final state. It is a form of matter that has been compressed by gravity as far as it is possible to go. It is a quiet and stable endpoint in the story of matter, a final, peaceful resting state from which no further change is possible. It is the end of the journey of compression. A black hole is a place where space is falling. This is a beautiful and simple way to picture what is happening around a black hole. According to some physicists, it is not that the object is pulling things in, but that the fabric of space itself is constantly flowing inward, like a river. The event horizon is simply the point where this river of space begins to flow faster than the speed of light. To fall into a black hole is to simply be carried along by this gentle, inexorable current. The event horizon is the point where space is falling faster than the speed of light. Imagine trying to swim upstream in a river. If the river is flowing faster than you can swim, you will be carried downstream no matter how hard you try. The event horizon is the point where the river of space-time is flowing inward faster than the maximum possible swimming speed in the universe, the speed of light. This is why nothing, not even a beam of light, can escape. It is a gentle cosmic current that cannot be overcome. Black holes have a temperature even though they are perfectly black. This is the profound discovery of Stephen Hawking. Due to quantum effects, a black hole is not completely cold. It radiates energy and therefore has a temperature. This temperature is a measure of the black hole's own internal state, a faint theoretical warmth that connects the laws of gravity with the laws of thermodynamics. It is a sign that even the darkest objects in the universe have a subtle, hidden glow. This temperature is incredibly low, far colder than the background temperature of space. For a black hole with the mass of our Sun, the temperature from its Hawking radiation is only about 1/1,000,000th of a degree above absolute zero. This is so much colder than the faint warmth of the cosmic microwave background radiation that fills all of space. This means that, in the current universe, all stellar mass black holes are actually absorbing more energy from the cosmos than they are emitting. They are growing colder, not warmer. A solar mass black hole has a temperature of less than 1/1,000,000th of a degree above absolute zero. This is a temperature so close to absolute zero that it is almost impossible to imagine. It is a state of almost perfect cold, a quiet and profound stillness at the quantum level. This makes stellar mass black holes some of the very coldest objects in the entire universe. They are places of deep, abiding and almost perfect cold. They are the coldest known objects in the universe. While places deep in space are cold and scientists on Earth can create temperatures very close to absolute zero in their labs, a large black hole is theoretically colder than any of them. Its temperature is so low, its thermal energy so faint, that it represents a state of near-perfect internal quiet. It is a place where even the quantum jitters of heat have been almost completely stilled. The shadow of the black hole in the famous photograph is 2.5 times larger than its event horizon. The dark circle we see in the event horizon telescope image is not the event horizon itself, but the black hole's larger shadow. This is because the black hole's intense gravity captures light from a much wider area. Any photon that passes within this larger region gets caught in an unstable orbit and spirals into the black hole. This larger capture cross-section is what creates the dark silhouette that we are able to see. The gentle darkness we observe is a larger, softer version of the boundary within. The universe contains different sizes of black holes, from stellar mass to supermassive. Black holes are not all the same. They come in a beautiful and diverse range of scales. There are the small, quiet, stellar mass black holes, the ghosts of individual stars. There are the colossal, supermassive black holes, the patient anchors of entire galaxies. And there may be the missing intermediate mass black holes and the ancient, tiny primordial ones. The universe is filled with a rich and varied family of these quiet, simple objects. The shadow of the black hole in the famous photograph is 2.5 times larger than its event horizon. The dark circle we see in the event horizon telescope image is not the event horizon itself, but the black hole's larger shadow. This is because the black hole's intense gravity captures light from a much wider area. Any photon that passes within this larger region gets caught in an unstable orbit and spirals into the black hole. This larger capture cross-section is what creates the dark silhouette that we are able to see. The gentle darkness we observe is a larger, softer version of the boundary within. This is because its gravity captures and bends light from a wider area. The intense curvature of spacetime around the black hole acts like a powerful lens, redirecting the path of any light that comes near. The black circle we see corresponds to the final photon orbit, the last possible path for light before it is irrevocably captured. This means the shadow is a direct and beautiful visualization of the black hole's gravitational influence on the light of the cosmos. It is a portrait of gravity itself, painted with light and darkness. The universe contains different sizes of black holes, from stellar mass to supermassive. Black holes are not all the same. They come in a beautiful and diverse range of scales. There are the small, quiet, stellar mass black holes, the ghosts of individual stars, perhaps 10 times the mass of our Sun. There are the colossal, supermassive black holes, the patient anchors of entire galaxies, weighing millions or billions of suns. And there may be the missing intermediate mass black holes and the ancient, tiny primordial ones. The universe is filled with a rich and varied family of these quiet, simple objects. A stellar mass black hole might be 10 times the mass of the Sun. These are the most common type of black hole, formed from the final silent collapse of a very large star. They are small and incredibly dense, with an event horizon only a few dozen miles across. They are the quiet, solitary remnants of a star's brilliant life, now drifting peacefully through the galaxy. They are the gentle, dark embers left over from the brightest stellar fires. A supermassive black hole can be billions of times the mass of the Sun. These are the gentle giants of the cosmos, residing in the heart of nearly every large galaxy. They are not just larger, they are fundamentally different, having grown over eons by merging with other black holes and accreting matter. Their event horizons can be vast, larger than our entire solar system. They are the calm, quiet centers around which the grand spiral dance of the galaxies unfolds. The largest black holes are found in the centers of the largest galaxies. There is a deep and gentle connection between a galaxy and the supermassive black hole at its heart. It seems that they grow together in a slow, symbiotic dance over billions of years. The more massive the galaxy, the more massive its central black hole tends to be. They are not separate entities, but two parts of a single, vast, and interconnected cosmic ecosystem. The black hole, TON 618, is one of the most massive objects ever discovered. Residing in the center of a distant galaxy, this ultramassive black hole is a true titan. It weighs an estimated 66 billion times the mass of our Sun. Its event horizon is so vast that a beam of light would take weeks to travel across it. It is an object of almost unimaginable scale, a quiet and gentle reminder of the upper limits of what the universe can create. It represents the universe in a state of ultimate gravitational peace. Its shadow would be large enough to swallow our entire solar system. The sheer scale of an object like TON 618 is difficult to picture. The dark silhouette it casts on the light behind it would be many times larger than the orbit of Neptune. It is a quiet, calm darkness on a scale that dwarfs all of our human experience. It is a gentle, cosmic ocean of serene and simple spacetime. Despite their power, black holes are a natural part of the cosmic ecosystem. They are not anomalies or monsters. They are a normal and necessary part of the universe's life cycle. They are the natural end state for massive stars and the quiet gravitational anchors for galaxies. They are as fundamental to the structure of the cosmos as the stars themselves. They are a quiet, gentle, and essential component of the universe's beautiful machinery. They are not monsters, but fundamental objects shaped by the laws of physics. Our fear of black holes comes from a misunderstanding of their nature. They are not malevolent, but are simply matter obeying the gentle, persistent, and inevitable laws of gravity. They are perfect passive objects, governed by the same elegant principles that keep the Earth in orbit around the Sun. They are a quiet expression of the universe's deepest and most fundamental rules. The key gravity of a black hole is just gravity behaving in an extreme way. There is no new or strange force at play. A black hole is simply what happens when you gather enough matter into a small enough space. It is the natural consequence of gravity's relentless nature. The quiet, gentle pull you feel from the Earth is the exact same force that, in its most extreme form, creates the silent, perfect darkness of a black hole. The journey of matter into a black hole is its final return to a state of simplicity. The universe is a place of incredible complexity, with matter arranged into stars, planets, and living things. The journey into a black hole is a gentle unwinding of this complexity. All the intricate structures and information are smoothed away, and the matter contributes only its most basic properties, mass, spin, and charge, to the whole. It is a quiet and peaceful return to a state of perfect, featureless grace. Black holes are a quiet reminder of the power of gravity. In our daily lives, gravity feels like a weak and gentle force, but black holes show us its true underlying strength. They are a testament to the fact that, given enough mass and enough time, gravity is the dominant force in the universe, capable of sculpting galaxies, ending the lives of stars, and even bending the fabric of spacetime itself. They are quiet monuments to the universe's most patient and powerful force. They represent a place of ultimate stillness. In a universe filled with motion and change, a black hole is an end point. It is a stable, unchanging object that can persist for trillions upon trillions of years. The matter within it has reached its final resting state, a place of quiet equilibrium from which no further change is possible. It is a small pocket of eternity existing within our transient and ever-evolving cosmos. A black hole's shadow is its final, gentle fingerprint on the cosmos. A black hole itself is invisible, but the shadow it casts is a real and observable thing. It is the black hole's way of interacting with the light of the universe, leaving a soft, dark impression on its surroundings. This shadow is a quiet and beautiful signature, a final, gentle trace of its presence, written in the language of darkness against a canvas of light. The study of black holes is a study of the edge of space-time. These objects are the ultimate frontier. They are the places where our understanding of space, time, and gravity is tested to its absolute limit. To study them is to stand at the very edge of the known universe and gaze into the profound mystery of what might lie beyond. They are a gentle and quiet invitation to explore the deepest questions of existence. They are a place where the flow of time becomes a downward cascade. The metaphor of a river is a powerful one for a black hole. Time, which we experience as a forward-flowing river, gently curves as it approaches the black hole. At the event horizon, that river of time turns and begins to flow downward into the black hole itself. The journey toward the singularity becomes the new and only direction of the future. It is a place where the very river of time has changed its course. The darkness of a black hole is the most complete darkness possible. It is not the darkness of a closed room or a deep cave, which are merely places where light is absent. The darkness of a black hole is a fundamental property of space-time itself. It is a region from which light cannot emanate. It is a perfect and profound absence of illumination, a quiet and gentle endpoint for light itself. They are a point of perfect silence in the noisy universe. The cosmos is filled with the light of stars, the energetic particles of cosmic rays, and the radio hum of distant galaxies. A black hole is an oasis of perfect quiet in the midst of this activity. It absorbs all that falls upon it, reflecting nothing, emitting nothing. It is a place of ultimate peace and stillness, a perfect and gentle silence in the grand cosmic symphony. A black hole is a gentle and patient feature of the cosmic landscape. Far from being a destructive monster, it is one of the most stable, simple, and long-lasting objects in the entire universe. It drifts silently through space, its presence felt only by the gentle curvature of space-time around it. It is a quiet and serene monument to the laws of physics, a place of profound and unending calm. Around a spinning black hole is a region where you cannot stand still. This area, just outside the event horizon, is called the ergosphere. Here, the black hole's immense rotation drags the very fabric of space-time around with it in a gentle, irresistible vortex. To appear stationary to a distant observer, an object within the ergosphere would have to travel faster than the speed of light against this current of space. It is not a force pulling you inward, but rather the river of the cosmos itself, carrying you along in a silent, cosmic waltz. It is a place where the universe insists on a slow, unending dance. Energy can be gently extracted from a spinning black hole. The theoretical Penrose process describes a way to draw power from the ergosphere's motion. A particle could enter this region and split in two. One fragment would fall into the black hole, while the other would be ejected with more energy than the original particle possessed. This extra energy is quietly stolen from the black hole's rotational energy, causing its spin to slow down by an infinitesimal amount over eons. It is a way to borrow a little power from the universe's quietest spinning top. The mathematics of a black hole contain a theoretical bridge to another place. The simplest mathematical solution for a black hole also describes an Einstein-Rosen bridge, what we now call a wormhole. This is a hypothetical tunnel through space-time, a gentle shortcut connecting one point in the universe to another, or perhaps even connecting our universe to a different one entirely. While these theoretical bridges are believed to be unstable and impossible to traverse, their quiet existence in the equations hints at the deep and strange possibilities hidden within gravity. They are a gentle what-if written into the fabric of the cosmos. Some physicists believe a black hole might not have a singularity, but a soft, fuzzy surface. String theory offers an alternative to the infinitely dense point. In the fuzzball model, a black hole is a tangled, compact ball of fundamental strings. It wouldn't have a hard edge or a central point, but would be a soft, information-rich object, like a ball of cosmic yarn. The event horizon would be this fuzzy surface, and the information of things that fall in would be gently woven into the threads of the fuzzball itself, never truly being lost. The ultimate darkness may be a soft and tangled nest of cosmic threads. A black hole's entropy, a measure of its hidden information, is connected to the size of its surface. A deep and beautiful principle in physics connects the information content of a black hole to the surface area of its event horizon, not its volume. This was a revolutionary idea, suggesting that information can be stored like a painting on a two-dimensional surface. It is as if the entire story of everything the black hole has ever consumed is written in a quiet, invisible script upon its silent boundary. The story of the inside is written on the outside. A black hole can launch a star at nearly the speed of light. When a pair of stars in a binary system drifts too close to a supermassive black hole, one star can be captured into a tight orbit, while the other is ejected with incredible force. This gravitational slingshot can fling the star out of the galaxy entirely, creating a hypervelocity star. These are lonely, speeding stars, silent projectiles launched by a close, quiet encounter with a galactic center. They are solitary travelers on a journey to the empty space between the galaxies. The light from an accretion disk can be separated into different colors by gravity. The light from the side of the disk spinning towards us is brightened and shifted towards the blue end of the spectrum. The light from the side spinning away from us is dimmed, and stretched into redder wavelengths. This relativistic beaming creates a distinctive and beautiful asymmetry in the glowing ring, a visible signature of the incredible speeds and the powerful gravity at play. It is a cosmic rainbow painted by the gentle interplay of motion and space-time. Nugget 128 of 170. A Blazar is a supermassive black hole whose jet is pointed directly at the Earth. When we look down the barrel of one of these immensely powerful jets of energy, the object appears incredibly bright and energetic. Though it is a serene and distant object, its perfect alignment with us makes it one of the most luminous phenomena in the known universe. It is a quiet, cosmic lighthouse whose brilliant beam happens to be sweeping directly across our small world. Black holes can be formed not just from matter, but from pure energy. A theoretical type of black hole, called a Kugelblitz, could be formed if enough pure energy, such as light, were concentrated into a single, tiny point in space. According to Einstein's equation, E just mc2, energy and mass are equivalent, so a sufficient concentration of light could, in theory, collapse under its own gravity to form an event horizon. It is a beautiful idea of a darkness born from the most brilliant, concentrated light. The universe will one day enter a black hole era. Far in the distant future, after the last stars have burned out and faded away, black holes will be the last remaining large objects in the cosmos. For trillions upon trillions of years, the universe will be a dark, cold, and quiet place, dominated by these silent, slowly evaporating gravitational remnants. It will be an age of profound peace and simplicity, a quiet and meditative end state for our universe. The final evaporation of a black hole is a very gentle and slow process. Hawking radiation is not a violent explosion, but an incredibly faint and patient release of energy. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate completely. This timescale is so vast that it makes the current age of the universe seem like less than a single heartbeat. It is a slow, quiet sigh that lasts for an almost eternal amount of time. The last moments of the last black hole will be the final light in the universe. As a black hole evaporates, it gets smaller and hotter. In its very final second of existence, a small black hole would release its remaining energy in a final, gentle flash of gamma rays. In the far distant future, these will be the very last energetic events to occur in the cold, dark, and empty cosmos. They will be the universe's final, soft and quiet fireworks. A black hole is the most efficient object in the universe at converting matter into energy. The process of matter falling through an accretion disk and releasing energy is up to 40% efficient, meaning 40% of the matter's mass can be converted into light and heat. By comparison, the nuclear fusion that powers a star like our Sun is less than 1% efficient. Gravity, it turns out, is a far more powerful and gentle engine than any other force in the cosmos. The quiet space around a black hole can be filled with a faint echo of its past meals. Even after a black hole has finished actively feeding, the light from its brilliant accretion disk can continue to travel through the cosmos. This light can reflect off distant gas clouds, creating faint light echoes that arrive at our telescopes thousands of years after the black hole itself has gone dormant. These echoes are a gentle, ghostly reminder of a time when the sleeping giant was once awake. The merger of two neutron stars can create a new black hole. When two of these super-dense stellar remnants spiral into each other and collide, the resulting object can be so massive that it immediately collapses under its own gravity. This event, which also creates a brilliant flash of light and a shower of heavy elements like gold, is one of the ways the universe seeds itself with both precious materials and new quiet black holes. It is a creative event born from a silent gravitational collision. A black hole's gravity can feel like a gentle tide. The stretching force of gravity is known as the tidal force. For a very large, supermassive black hole, this force is extremely gentle at the event horizon. The experience of falling in would not be a violent pull, but a slow, inexorable, and peaceful stretching, as if being drawn out by a soft and silent cosmic tide. It is a quiet surrender to the gentlest and most powerful current in the universe. A black hole has no memory of what it was made from. This is the essence of the no-hair theorem. Whether it consumed a star made of hydrogen or a planet made of diamonds, the resulting black hole is identical. All the intricate details are quietly forgotten. This makes black holes the purest objects in the universe, defined not by their history, but only by their present simple state of being. The path to a black hole is a journey toward perfect simplicity. The universe around us is full of complex structures and chaotic interactions. A black hole is the opposite. It is an object of perfect mathematical elegance and calm. The journey towards one is a journey away from the noise and complexity of the cosmos toward a place of profound and simple quiet. Even empty space near a black hole has a gentle energy. The intense curvature of space-time near an event horizon can cause quantum fields to behave in strange ways. According to some theories, this can create a state of vacuum polarization, where the empty space itself is imbued with a subtle energy. The quiet space at the edge of a black hole is not truly empty, but is filled with the gentle, theoretical hum of quantum potential. The gravitational field of a black hole can be thought of as stored information. Some physicists have begun to think of gravity not as a force or a curvature, but as a form of information. In this view, the shape of space-time around a black hole is a kind of vast, silent storage device with the information about the black hole's mass and spin encoded in its gentle, geometric curves. The black hole's story is written in the quiet language of space-time's shape. The idea of a black hole teaches us about the nature of nothingness. A black hole's interior is a region of space-time, not a solid object. It is a place where a tremendous amount of mass has created a profound and inescapable emptiness. By studying black holes, we learn about the properties of the vacuum and the deep connection between matter, space, and time. It is a gentle exploration of the most profound kind of nothing in the universe. A dormant black hole is one of the most peaceful places in the universe. A black hole that is not actively feeding on gas or stars is in a state of perfect equilibrium. It is not emitting light or energy. It is simply resting, its presence felt only by its gentle, constant gravitational field. The space around it would be cold, dark, and profoundly silent. It is the very definition of cosmic tranquility. The darkness of a black hole is not empty. It is full of curved space-time. We think of darkness as an absence, but the shadow of a black hole is a place of immense presence. It is a region where space-time is so profoundly warped that it has folded in on itself. The darkness is not a void, but a place filled with the silent, invisible, and powerful substance of gravity itself. Black holes help astronomers weigh distant galaxies. By observing the speed of stars and gas orbiting the center of a galaxy, astronomers can calculate the total mass needed to hold them in their orbits. The speed of the innermost stars reveals the mass of the central supermassive black hole with beautiful precision. The black hole becomes a quiet, gravitational scale for weighing an entire city of stars. The first black hole to be confirmed was discovered in a silent orbital dance. The object known as Cygnus X1 was first noticed as a powerful but invisible source of X-rays. Astronomers then saw a bright blue supergiant star orbiting this invisible point. By studying the star's gentle periodic wobble, they were able to confirm that its unseen partner was far too massive to be a normal star, providing the first solid evidence for the existence of black holes. Its presence was revealed by the quiet, rhythmic sway of its companion. A black hole's event horizon acts like a perfect one-way membrane. It allows matter and energy to flow gently inward, but allows absolutely nothing to flow outward. This perfect directional property is unique in all of physics. It is a gentle cosmic valve, ensuring that the flow of things in this one particular part of the universe proceeds in only one quiet and final direction. Black holes are the natural end of a story that begins with gravity. The same gentle force that caused the first dust clouds to clump together, that formed the first stars, and that holds planets in their orbits, is the same force that, in its most complete expression, creates a black hole. They are not a strange deviation from the story of the universe. They are its quiet, logical, and peaceful conclusion. The quiet region inside a spinning black hole is mathematically stable. Unlike the singularity of a non-spinning black hole, the ring-shaped singularity of a rotating one is a place you could theoretically approach without being destroyed. While it is a purely mathematical idea, it paints a picture of the interior of a black hole as a place with a complex and perhaps even a gentle structure, a hidden landscape of space-time hidden behind the quiet veil of the event horizon. And so, our gentle journey to the quiet edges of space-time draws to a close. We have drifted through the silent gravitational fields of black holes, and we have found not terror, but a deep and profound sense of peace. The echoes of these ideas can now begin to soften and fade, leaving only a feeling of calm stillness in their place. It is time to let it all go. We have wandered through a universe where time can slow to a gentle halt, where silence is absolute and where the most complex things in the cosmos can return to a state of perfect simplicity. We have felt the quiet dance of orbits, the soft whisper of gravitational waves, and the serene, unchanging nature of these ancient and patient objects. Let the feeling of this vast and quiet simplicity be a comfort to you now. The same gentle laws of gravity that create these silent, distant objects are what hold you softly to your bed. The universe that contains these profound mysteries is the same one that contains you. You are a part of this grand and beautiful cosmos, a temporary and intricate pattern in the same fabric of space-time that can curve so gracefully into a black hole. You belong here, and now, as you drift down into the soft and welcoming darkness of sleep, there is nothing left to do. Let these thoughts dissolve like starlight in the morning sky. Let the idea of the black hole be a comfort, a symbol of ultimate quiet and stillness. Your only task now is to rest, to let go of the day, to allow your mind to become as calm and quiet as the space between the stars. May your sleep be deep and your dreams be peaceful. Good night.